We will now move on to the next subtopic of chapter on simple harmonic motion, which is the kinematics of simple harmonic motion. Previously, we were talking about the criteria that you need to achieve in order for an object to be undergoing simple harmonic motion. But now we are focusing only on simple harmonic motion, and we are going to study how the object moves for simple harmonic motion. So when we want to describe how an object moves, we'll describe it using displacement, we'll describe it using velocity, we'll describe it using acceleration. So in this subtopic over here, we'll be discussing how to relate between displacement and time, velocity and time, and acceleration and time. So this is similar to what you do in your chapter 2 on kinematics of linear motion. But now this is for simple harmonic motion. Okay, so here I have a spring mass system. And of course, this spring mass system here will be oscillating between x equals to negative a and x equals to positive a. So I want all of you to try and carefully observe how does the object move. Okay, and while you see how this object move, also notice how do I plot the graph for this displacement against time graph over here. The x, sometimes you can call it position, we can call it displacement as well, because we start at the equilibrium position. So the position and the displacement are the same thing over here. Okay, because we set the equilibrium position as our initial position and our origin as well. Okay, so for this system over here, the object will start from the equilibrium position. As you can see, I place my blue object over here at the equilibrium position, and it will start by moving toward the positive direction first. So you should expect this object will be moving towards this direction. Okay, remember when you plot this graph over here, if the object is at somewhere further away from the equilibrium position, if it's far away from the equilibrium position, then you have a larger value. Okay, it's either larger value at the negative side or the positive side. Further away, larger value. Then if the object is at the right hand side of the equilibrium position, that means the displacement is a positive displacement. So as long as the object is around this region, you should expect the displacement to be a positive displacement. Whereas if our object is at this side of the equilibrium position, the negative side, you should expect the displacement to be below the time axis because it's a negative displacement. So larger value means further away, above the time axis means it's towards the right, below the time axis means it's towards the left. Okay, so now let's start and observe how these things move, and at the same time observe how I plot this graph over here. So let's start. Okay, so basically this is what a displacement time graph tells you. The displacement time graph tells you at each different moment where is the object, whether it's somewhere far away from this equilibrium position, or it's somewhere near to the, or it's somewhere on the equilibrium position, or somewhere in between the amplitude and the equilibrium position. Let's say somewhere around here. So by plotting the position of the object at each different moment, we can see that these dots over here are tracing a sine curve actually. So therefore, to describe this simple harmonic motion here, we can describe it using a sine curve. Therefore, we should expect the equation that relates between the displacement and the time to have a sine inside it. Okay, so we know that this amplitude, this maximum positive displacement and negative displacement are positive amplitude and negative amplitude respectively. We have discussed this in the parameters video earlier. So from here, we know that the equation to describe this graph and to describe this motion here will be x equals to a, the amplitude, which is over here, and sine, because the shape of the graph is a sine curve, and omega t. Omega t here, how do you get omega? Omega is 2 pi over period, right? So period will be the time from here to here. So the time duration from the start over here until this point here, it's the period. You can take from here to here, also a period. or you can take from here to here also a period. Basically, the time taken to complete one cycle. So 2 pi divided by the period times the time will be what we put inside the bracket. Because when your time goes towards period, when you have finished one cycle, your t will be equals to period. So 2 pi divided by period times period will become 2 pi. So sine 2 pi will become 0. Okay, so this is a rough idea why it's an omega t inside. Okay, so let's move on to the second situation. Notice what's the difference between the first system and the second system over here. The difference is the way we start the oscillation. Previously, the object is at the equilibrium position and we move towards the positive direction. Now, for this system, the object is at the positive maximum displacement first. The object is now at the furthest away distance from the equilibrium position. It is somewhere over here. It will start its motion from here. So if you start your motion from here, you start by moving towards the equilibrium position. So you'll be moving in the negative direction towards negative A. Okay, so the way we start is a bit different. And if you see it, you'll be moving like this. Okay, so since this spring mass system here starts from the positive amplitude, then you should expect this graph here to start from somewhere here. Okay, at time equals to 0, you should start at the positive amplitude. For the system, the first system here, the object starts at the equilibrium position as seen over here. But for the second system here, the object starts at the positive amplitude. So you should expect the graph to start from here and you oscillate towards the equilibrium position, then you go away, something like this. Okay, so if you draw the graph, it should be something like this. Starting from the positive amplitude, moving towards the equilibrium position, then move towards the negative negative A, because it goes from here towards negative A. Then from negative A, you go towards equilibrium position, then towards positive A, then it goes up like this. Then you repeat again and again because it's a periodic motion. Okay, so for this graph over here, you can describe it as a cos graph because this is a cosine shape, right? Therefore, your equation should be A cos omega t. Okay, so there is no fixed equation to relate between displacement and time. You have to look at how does the oscillation starts. If the oscillation starts from the equilibrium position and it starts by moving in the positive direction first, then it will be a sine curve. But if it starts at the positive amplitude, then it will be a cos curve. And now we look at other two examples. If it starts at the equilibrium position, but it moves towards a negative direction first. So instead of moving this way, it moves to the left first. So if you move towards the left first, then your graph will be different from just now. Okay, so this is the motion. You know that you move towards the left first. So you should expect the graph to go this way. Instead of upwards first, you go downwards like this. So the shape of the graph will be like this, and this is a negative sine curve. So therefore, your graph here should have an equation which is negative sine omega t. Negative sine because the shape is negative sine. Again, the maximum is still the amplitude, so this is still A over here. Okay, so next, the system over here, it starts from the negative amplitude. If it starts from a negative amplitude, then the graph, the motion will be towards positive, back towards negative amplitude, towards positive, back towards the initial position. So now you should expect the graph to start from the negative, the maximum negative displacement over here. Then you start by moving towards the equilibrium position, right? So the graph should trace something like this. From negative A, go up towards 0, then go towards positive A, 0, then negative A, 0, positive A, something like that. So you should expect your graph to be like this. So this is a negative cos graph. So your equation will be x equals to negative A cos omega t. The shape of the graph dictates whether it's negative or positive, cos or sine. But it's always A because the maximum and the maximum amplitude, no matter positive or negative, it's always A, whether it's just positive A or negative A. Then omega t, it's fixed, okay, because it's 2 pi over period inside. Okay, so that's how you create an equation based on the motion, and that's how you create a graph based on the motion. Always be careful with how the motion starts. Starting from the equilibrium is different from starting at the positive or negative maximum displacement. And starting at the equilibrium position, you also need to look whether it starts by moving in the positive direction first or moving in the negative direction first. So this is how you determine the shape of the graph and the equation of the graph. So in the next video, we'll be talking about something which is slightly out of the syllabus, which is on the idea of phase angle. What if it doesn't start from the center, the equilibrium position? What if it doesn't start at the maximum displacement? What if start at somewhere in the middle around here or somewhere in the middle around here? How do we take into account this kind of situation? That we will leave it to the next video.